Hello. I'm going to summarize some of the ideas we've discussed when working with systems of two equations and two unknowns. I'm going to begin by talking some more about special cases. And then I'm going to do several examples where I can compare and contrast the three common solution methods. So let's begin by talking about special cases. First thing I want to discuss is some new terminology. Look at the heading on this slide, 2x2 systems of equations. This is frequently used language when we're talking about two equations with two unknowns, 2x2. Systems of equations that simplify or add to false statements are inconsistent. Inconsistent systems have no solutions. False statements are statements that equate two unequal numbers. For example, 0 equals 8. I need to tell you that it's really important that you purposefully memorize this terminology. You need to memorize that inconsistent systems have no solutions and that you recognize inconsistent systems by equating the system to a false statement. The reason it's so important that you memorize these words is because when you hear us use these phrases and words in later lessons, you want to know what it is we're talking about. Systems of equations that simplify or add to an identity have infinitely many solutions. The equations in the system are dependent. One type of identity equates two equal numbers. For example, 7 equals 7. Here again, you need to actively memorize all of this vocabulary and ideas. The solution set to a system of dependent equations is the set of all points on the common line that represents the solution set to each equation in the system. Now I can remember being in math class and my teacher throwing a sentence like that up on the board, and my reaction was sort of along these lines. Huh? So, let's see what these words mean. Let's solve the system y equals 2x minus 1 and 6x minus 3y equals 3. There's something new and different about this problem from the examples you've seen Candace and Ann work. We weren't told the method to use to solve the system. We have three common methods to choose from: the graphing method, the substitution method, and the elimination method. I generally stay away from the graphing method for all sorts of reasons that I'm going to discuss later on. So I'm going to pick between the substitution method and the elimination method. It's my choice. The first equation is solved for y, so I think I'm going to go ahead and use the substitution method. So I'm going to begin by substituting 2x minus 1 for y into the second equation. And when I do that, the second equation becomes 6x minus 3 times 2x minus 1 equals 3. Let's solve for x. Distributing the negative 3 through the parentheses on the left turns the left side of the equation into 6x minus 6x. Negative 3 times negative 1 is plus 3. This all equals 3. When I combine my x terms on the left, they go away. They add to 0. And I'm just left with the equation 3 equals 3. This is an identity. 3 always equals 3, regardless of the values of x and y. This is a signal that I have a dependent system of equations. The two equations should graph to the same line. One way I could check this is I could put both equations in slope-intercept form and show that the two equations are equivalent to the same slope-intercept form equation. I'm going to do that in a later example. But in this example, I'm actually going to do my check graphically just to remind you visually what it is that is occurring with this system. So I've gone ahead and had the computer graph the first equation for me, y equals 2x minus 1. Let's verify that this line is accurate. We should have a line that passes through the point 0, negative 1. Here's the point 0, negative 1. We also should have a line that has a slope of 2. we can think of 2 as 2 over 1. Let's do a rise of 2 and a run of 1. Up 2, right 1. Boy, we've got another point on the line. So it looks like the computer did a pretty good job of graphing this line for us. So what we're going to do is we are going to find 2 points on the line 6x minus 3y equals 3 and verify that those 2 points are also on the line y equals 2x minus 1. When y is 1, what's the value of x on 6x minus 3y equals 3? Well, when we replace y with 1, we would have 6x minus 3 equals 3. Adding 3 to both sides of the equation, we'd have 6x equals 6. And dividing both sides of the equation by 6, we'd just be left with x equals 1. How about when y is 5? Well, we'd have 6x minus 15 equals 3. Adding 15 to both sides of the equation, I'd have 6x equals 18. And dividing both sides of the equation by 6, I'd just be left with x equals 3. Now, I just did a whole lot of algebra and arithmetic in my head. A lot of you would probably have more success if you got out some scratch paper to work through those steps, or even on your test, carefully work the steps on your paper. That's great. Do what works for you, because the #1 issue is we want you to be successful. Now let's go ahead and plot these points. We have the point 1, 1, and we have the point 3, 5. Check it out. Both of those points lie on the line y equals 2x minus 1. If I connect those points, look what I get. I get the same line as y equals 2x minus 1. Let's go ahead and state our conclusion. The system has infinitely many solutions. The solution set is the set of all points of the form x, y that have the property that the y-coordinate equals 2 times the x-coordinate minus 1. Let's do another example. Let's solve the system negative 2y equals 4x plus 4 and 4x plus 2y equals 8. This time, I think I'm going to use the elimination method. So I'm going to begin by writing the first equation in standard form, which entails subtracting 4x from both sides of the equation. When I do that, I get minus 4x minus 2y equals 4, and my second equation is 4x plus 2y equals 8. If I just go ahead and add the 2 respective sides of the equations together, the x's will be eliminated. So let's do that. Negative 4x plus 4x, that's 0x. Negative 2y plus 2y looks to me like we got a 2-for-1 special. Y was eliminated as well. That's 0y. All we're left with on the left side is 0. On the right side, we have 4 plus 8, which is 12. I don't think 0 equals 12. It doesn't matter how hard I try. I'm not going to find a value of x and a value of y that makes 0 equal 12. This is a false statement. Consequently, it must be the case that the system of equations is inconsistent. The system of equations has no solutions. But I still need to check this. And the way I'm going to check is I'm going to establish that the 2 lines actually are parallel lines. Parallel lines never intersect. How do I establish this? I do it by writing each of the 2 equations in slope-intercept form. So let's do that. I'm going to start with the equation on the right, 4x plus 2y equals 8. When I subtract 4x from both sides of the equation, I get 2y equals 8 minus 4x, and dividing both sides of the equation by 2, I have y equals 8 over 2, which is 4, minus 4x over 2, which is minus 2x. So I have a slope of negative 2 and a y-intercept 0, 4. How about the other equation? Well, what I need to do is I need to divide both sides of the equation by negative 2. So let's do that. Negative 2y divided by negative 2 equals 4x divided by negative 2 plus 4 divided by negative 2. So on the left, I'm just left with y On the right, negative 2 goes into 4x negative 2x times, plus negative 2 goes into 4 negative 2 times. So I think I'm going to write this as minus 2. So what do I have? I have a slope of negative 2, and I have a y-intercept 0, negative 2. The slopes of these two lines are equal, so the two lines are either parallel or, in fact, two representations of the same line. Since the y-intercepts are different, the two lines must be parallel. They never intersect. Let's see that. Here, I have the line y equals minus 2x plus 4. Here I have the line y equals minus 2x minus 2. These two lines never intersect. The system has no solution. The system has no solutions. We say that the system is inconsistent. So let's compare and contrast the three common methods for solving systems of two equations with two unknowns. Let's begin with the graphing method. Let's discuss an advantage. An advantage is that it's fairly easy to visualize what the heck it is we're talking about. Are there disadvantages? You betcha. It's difficult, if not impossible, to find exact solutions. If both coordinates of your solution are not integers, it's almost impossible to determine the solution graphically. And unless you're a master grapher like Candace, you might not even be able to figure out the solution when both coordinates are integers. So that's a major drawback on the graphing method. How about the substitution method? What's an advantage? Well, the substitution method is fairly easy to use if one equation is already solved for one of the two variables and there are no fractions involved. And you can find the exact solution using the substitution method. What's the disadvantage? The disadvantage is that the arithmetic can get really messy really quickly. We're going to see some examples of that. Something else that's important to know about the substitution method is that the substitution method can be used on nonlinear systems. We're going to see some examples of that later on in your math courses. We're giving you practice in linear systems so that when you do encounter other places where you want to use the substitution method, you've already kind of boned up the skill. How about the elimination method? What's some advantages? Well, it's as easy as it gets. Now, I'm not saying that it's easy. I'm just saying of the two algebraic methods, the elimination method generally can be easier than the substitution method, and it all has to do with fractions. So what's the disadvantage? The disadvantage is that the elimination method doesn't give you as much practice with fraction arithmetic as you get with the substitution method. Now, I know what a lot of you are thinking. A lot of you are thinking, hot diggity dog, that sounds good to me. I think I probably agree with you. All right, let's see an example. I think I'm going to solve this system using the elimination method. The coefficients on x are 2 and 5. Neither of those numbers evenly divides into the other number. The coefficients on y are negative 3 and negative 4. Neither of those numbers evenly divides into the other number. When you don't have even division going on, that's the situation where you want to think about multiplying the first equation by one number and the second equation by a different number to create opposite coefficients on one of the variables. Let's focus on x. The coefficients are 5 and 2. The least common multiple of 5 and 2 is 10. So I want to multiply by numbers that's going to result in 10x in one of the equations and negative 10x in the other equation. I can do that if I multiply both sides of the first equation by 2 and both sides of the second equation by negative 5. Let's do that. 2 times 5x minus 3y equals 2 times 8, and negative 5 times 2x minus 4y equals negative 5 times negative 3. When I multiply both sides of the first equation by 2, I get the equivalent equation 10x minus 6y equals 16. when I multiply both sides of the second equation by negative 5, I get the equivalent equation, negative 10x plus 20y equals 15. Let's add the respective sides of the two equations. 10x minus 10x, that's 0x. X has been eliminated. That's the whole reason I just went through those motions. Negative 6y plus 20y, that's 14y, and that equals the sum of 16 and 15, which is 31. So dividing both sides of the equation by 14, I have a y value of 31/14. Let's see what x has to be if y is 31/14. So when y is 31/14, let's go ahead and use the second equation to find the value of x. Why am I using the second equation? Because the numbers just look a little smaller to me, so I'm going to make it as easy on me as possible. So when y is 31/14, we have 2x minus 4 times 31/14 equals negative 3. So 2x equals, 4 and 14, they have a common factor of 2. So the fraction reduces when I multiply 4 and 31/14, but I'm going to go ahead and leave the denominator as 14 because the denominator in y is also 14. So when I do my check, it's going to be a little bit easier if I already have a common denominator. So I've got 2x equals, let's see, what do we have? We have 4 times 31 is 124, so I need to add 124/14 to both sides of the equation. And then I need to subtract 42/14. That's the equivalent 14ths of 3. So this gives me 2x equals, what do we got going on here? 82/14. And dividing both sides of the equation by 2, I have 82/2 is 41 in the numerator and 14 in the denominator. Let's go ahead and check this solution. If x is 41/14 and y is 31/14, then let's see what the left side of the first equation simplifies to. We have 5 times 41/14 minus 3 times 31/14. I'm writing these integers over 1 just because it helps me line up my fraction multiplication. We have a common denominator of 14 here. 5 times 41 is 205. That's the first numerator. Minus 3 times 31, that's 93. That's the second numerator. So let's see, when I perform the subtraction in the numerator, I get, what do I get? 112. So the numerator's 112, the denominator's 14. Now, I wanted 5x minus 3y to equal 8. So I'm going to be kind of sneaky. Rather than figuring out what 112 divided by 14 is, I'm just going to multiply 14 by 8 and make sure that's 112. 14 multiplied by 8 is 80 plus 32, which is 112. This is 8, which is what I wanted 5x minus 3y to equal. Let's check the other equation. And we've got 2/1 times 41/14 minus 4/1 times 31/14. So again, I've got my common denominator of 14. The numerators end up subtracting to 82 minus 124. 82 minus 124 is negative 42. Now, the right side of the second equation is supposed to be negative 3. What do we get if we multiply 14 and negative 3? We get negative 42. So negative 42 divided by 14 is negative 3. This checks. So let's go ahead and write our solution. The solution to the system is the ordered pair 41/14, 31/14. Now, what would have happened if we had tried the substitution method? Well, if we solved the first equation for y, we would get y equals 5/3 x minus 8/3. And when we substituted that expression into the second equation, replacing y with 5/3 x minus 8/3, this is the equation we'd have to solve. And if you ask me, the ick factor on this equation is pretty high because of the distribution and the fractions. Let's see what the computer's opinion is. Let's get out the old ick meter. Boy, even the computer thinks this one's pretty icky. It's a little bit more than a 6. How about if we solve the second equation for y? We get y equals 1/2 x plus 3/4. Substituting 1/2 x plus 3/4 for y in this first equation, we'd have to solve this equation for x. This is even ickier. Why is this one even ickier? Now we don't even have common denominators in our two fractions. What if we solve the first equation for x? When we substitute it into the second equation, we'd have to solve this equation. We're back to about a 6.5 on the ick meter. How about if we solve the second equation for x? When we substituted that expression into the first equation, we'd have to solve this equation. This equation is not so bad. There's only one fraction. It has a denominator of 2. But we can make it even less icky because when we did the addition method, the first thing that we did was we created the common coefficient on x, then we added the two equations, and then we divided both sides of the equation by 14. It's true that we ended up with a fraction. You can't avoid that. If the answer has a fraction in it, the answer has a fraction in it. But what we did do was we avoided any fraction arithmetic on our path to discovering this fractional answer. This is almost a 0 on the ick meter if you're thinking about fractions being icky. All right, let's work another example. In this system, y has already been solved for, so I think I'm going to use the substitution method. So substituting 5x plus 7 for y in equation 2, we have 3x minus 2 times 5x plus 7 equals 7. Distributing, we have 3x minus 10x minus 14 equals 7. Combining like terms, minus 7x minus 14 equals 7. Adding 14 to both sides, negative 7x equals 21. Dividing both sides by negative 7, x is negative 3. What's our y value? Well, if x is negative 3, from our first equation, we see that y is 5 times negative 3 plus 7, which is negative 8. Our solution appears to be the point negative 3, negative 8. Let's check. If x equals negative 3 and y equals negative 8, then 5x plus 7 is 5 times negative 3 plus 7, which is negative 8, which is y. So the first equation checks. And 3x minus 2y is 3 times negative 3 minus 2 times negative 8. That's negative 9 plus 16, which is 7. We wanted 3x minus 2y to equal 7, so this checks as well. The solution to the system is indeed the point negative 3, negative 8. Now, what would have happened if we had tried the elimination method? Well, the first thing we would have to do is write the first equation in standard form. And then we could create a common but opposite coefficient on y by multiplying both sides of the first equation by 2. We'd add them up, and that would give us x equals negative 3. Compare that to the work we did to find x equals negative 3 using the substitution method. It looks like a pretty equal amount of work to me. So this is truly a place where it's just a matter of personal preference. It's whichever method you prefer to use. Let's do one last example. Now, I know one thing that's going through your head, and that's that the ick meter is through the roof on this problem because there's fractions all over the place. Just like you can't avoid fractions in answers, you also can't avoid fractions in stated problems. If there's fractions in the stated problem, there's fractions in the stated problem. But how could we reduce the ick meter? A way we could reduce the ick meter is we could eliminate the fraction from both equations in the system before we set about trying to find the solution to the system. So let's do that. We can eliminate the fraction of 5/2 in the first equation if we multiply both sides of the first equation by 2. In the second equation, my fractions have denominators 12, 3, and 2. The least common multiple of 12, 3, and 2 is 12. So I can eliminate the fractions if I multiply both sides of the equation by 12. Now I'm going to do this pretty quickly because I'm running out of time. You want to sit down and carefully check my work on your own. 2 times 5/2 x is 5x, minus 2 times 2y is minus 4y, equals 2 times -3, which is -6. 12 times -5/12 is just -5, so we have -5x. Y over 3 times 12, 3 goes into 12 4 times, so that's plus 4y, and 12 times 1/2, that's 6. Hey, check it out. When we cleared these fractions, we got a bonus. We already have opposite coefficients on x. So when we add the two respective sides, x is going to be eliminated. Let's do it. 5x minus 5x is 0x, minus 4y plus 4y is 0y. We have another 2-for-1 special. Both x and y have been eliminated. We're left with 0 on the left. -6 plus 6, that is also 0. Check it out. We got the equation 0 equals 0. 0 does equal 0. This is called an identity. When you perform the elimination or substitution method and you end up with an identity, that's a signal that you have dependent systems. But you still need to check. And let me tell you, especially in this case, why it's so important you check. Here's a common mistake people make. They're doing the substitution method, they solve the first equation for y, and then they substitute the expression they get back into the first equation. If you do that, you always end up with an identity. You think you have dependent equations when actually you've just made a flub-a-dub. We'll check to make sure we didn't do a flub-a-dub by making sure that the slope-intercept form for both these equations is indeed the same. So the equation on the right, let's go ahead and solve for y. Adding 5/12 x to both sides of the equation, we have y over 3 equals 1/2 plus 5/12 x, and then multiplying both sides of the equation by 3, on the left, I'm just left with y. On the right, I have 3/2 plus 3 goes into 12 4 times, so 5/4 x. How about the other equation? Subtracting 5/2 x from both sides, I have minus 2y equals minus 3 minus 5/2 x. Dividing both sides of the equation by -2, I have y equals -3 divided by -2 is positive 3/2. -5/2 divided by -2 is the same as -5/2 times -1/2. That is plus 5/4. That's the coefficient on x. The slope-intercept form of the first equation is y equals 3/2 plus 5/4 x. The slope-intercept form of the second equation is y equals 3/2 plus 5/4 x. These two equations do in fact graph to the same line. So let's go ahead and state our conclusion. The solution set to the system is the set of all ordered pairs x, y with the property. Let's go ahead and remind ourselves what the property was. Y has got to equal 3/2 plus 5/4 x. And that concludes Lesson 2.